delegates, and my fellow industry professionals. It's an honor for me to present our work here today. I'm Aniket Gaikwad from Haber, and today I'd like to share an idea that has shaped our approach for digital transformation. As AI adoption grows, the opportunity to use mill data is also increasing. But despite all this momentum, we have observed that 85% of AI projects fail. Throughout our work, we have realized that the biggest bottleneck towards AI is not any algorithm, it's the quality and the structure of underlying data foundation. So let's understand this better. If I ask you, can you tell me what were the process conditions for the 50 best batches in the last quarter that achieved both kappa viscosity targets simultaneously? Well, most mills can't answer this. Not because they don't have data, it's because their data is fragmented. So the 5 problems that you see here prevent us from connecting all this data to a single batch. Once we close this gap, our problems can be answered easily. We all know the challenges that our industry is facing today, and AI is getting a lot of attention for it, and rightly so. It does have potential for it. But in reality, the actual work doesn't begin from AI models. It begins from data foundation. The core principle behind this is simple. First, build the data foundation, and then AI models. Because a simple model that is built on good contextualized data will always outperform a sophisticated model that is built on fragmented data. Because we believe that data discipline is not just the first step, it is the foundation that makes AI successful. And this is very important in Indian context where process variability is high. In India, we use a variety of fibers, from agri-residues to recycled fibers to mixed hardwood softwood furnishes. Same recipe gives different results for different furnishes. That's why process context becomes very important here. Also, we use older equipment, so manual data isn't optional. It becomes our primary data source. We believe that the data variability shouldn't limit yourself from creating your data foundation. In fact, it's the strongest reason to build it. And here's how you can build it. So at Haber, we have developed this 5-step data foundation framework. No new sensor, no TCS upgrade, no capital investment. Just structured discipline to what mill already has. And here's how you can do it. So step 1 is identifying the critical variables. So this can be the variables like kappa number, viscosity, brightness, and the parameters that actually impact them. Second is standardizing measurement cadence, so that data from across batches, shifts, grades can be easily compared. Third is digital capture at source, so that you can actually trace your data and reduce any manual transcription error. The fourth step is contextualizing data. So here you can give as much context to your data as possible. So that can be your grades, shift, raw materials, process conditions, everything. And our final step is integrating all of this. So your historian data, logbook data, or DCS, QCS, all data to form a unified data layer. So to better understand these steps, let's look at the case study that we actually worked on. So the mill that we worked on operated on sulfide digestion process with 6 batch register. Their main objective was achieving consistent pulp quality. And the main KPIs they were focusing on were kappa number and viscosity. So the question that we essentially set out to answer was what were the process conditions that consistently achieved kappa target of 14 to 60 and viscosity target of 220 to 260. The mill had good amount of data. So we, after data cleaning and data frequency update, we used around 4,000 digester batches spread across 8 months. So to make this project successful, we set out 3 major deliverables here. First was identifying the golden batches. Second, define the operating envelope as a per digester recipe. And third, recommend these, translate these insights so operators and process engineers can actually use them as a recommendation. Since mill had good amount of data, but it was fragmented across different sources, so we had to implement our 5-step data foundation framework here. So we started with step 1, that is variables that matter. That means identifying variables that actually matter. So here, from thousands of tags from historians, logbook, DCS, QCS, we identified few variables that actually impacted kappa number and viscosity. So majorly they were related to sulfur dioxide dosage, sulfur dioxide concentration, chip moisture, time at maximum temperature, cooking time. Then we move to step 2, that is standardizing measurement cadence. Here we faced 3 problems before standardization. First was missing batch context. So few batches had no entries about the grades or operating conditions or the raw materials that they were made from. Second, inconsistent measurement frequency. So batch A had like 2 entries, batch B had 6, batch C had 3. And third, inconsistent recording format. So these were the 3 problems we faced before standardization. And solution for this was one standard operating procedure. So we developed one standard operating procedure. So one variable will have only one sampling measurement cadence, one recording format across all 3 shifts. Now this standardization can further be improved if we can capture this data digitally at source with correct timestamp. And for this we implemented our Mount Fuji platform's e-logbook here. And this is how it looks like. So here operator can select the batch, the digester, and enter corresponding value and enter with correct timestamp. And on your right you can see what it looks like. So if in a shift there are multiple batches, operators, process engineers can easily compare them. Something which is very difficult in paper logbooks. So now such digital tools will work only if they are easy to use or users can actually find them consistent to use. In our case, the user was operators. So 3 things mattered here. Operator needed to understand that their data mattered. This should be easier than the paper logbooks, and operator needs to see the impact of their data generated in the real batch. So in our case, operators were very happy, and they found that Mount Fuji logbook was very easy and handy, and they were able to capture all timestamp at the stop. They were able to capture all the data at timestamp. Now we move to step 4, that is giving context to data. So here all the data from historian, DCS, QCS were connected through one batch ID. So that batch particularly carries its entire history. So if in a batch a particular KPI was achieved or particular quality parameters was achieved, we can actually track back and see what were the process conditions or what was the raw material used to achieve that particular batch. Now we move to our step 5, that is connecting everything together. So all our data from historian, DCS, QCS, logbook, all needs to be connected to form this unified data layer called knowledge graph. And this is how it looks like. So here every sensor reading, every quality parameter, every logbook entry can be related to show how it looks like and how it flows into. So once we have all this analysis in place, let's look at what once we have all this foundation in place, let's look at what the analysis actually showed look like. So our central finding was related to looking at kappa number and viscosity together. So we found that kappa number was in range for almost 72.2% of the times, but viscosity was a big fluctuation, only 26.5% of times, and both together only 23%. One peculiar observation that we had here was this was consistent across all 6 batch digesters. So the problem was not related to any equipment or any digesters. So if we could optimize process completely, we could implement it across all 6 digesters. So ideally we looked at what these golden batches look like, and we found that one of the key findings was related to chip moisture. So conventionally Mill had thinking that lower chip moisture was better, but data showed the other thing. We found when we grouped 4,000 batches with moisture, we found that the lower moisture quartile showed around 14.25% golden batch percentage, while higher moisture quartile showed around 25.6%, nearly double. This was something that Mill had not expected. So we showed them this. So we recommended to maintain a minimum of at least 38% chip moisture. This is something that requires no capital investment, just optimizing the process and communication with the good yard. Our second finding was related to time at maximum temperature, because chip moisture is something that operators cannot control, but time at maximum is something that operators can control during the cooking process. So here, as the scatter plot shows, the time at maximum was more related to, or the time at maximum was more related to viscosity. So here we can reduce the time at maximum, that is actual cooking time, and without affecting kappa number. So this was because there are two major KPIs and both KPIs had two levers. One was sulfur dioxide dosage and other was just time at maximum. So time at maximum was more related to kappa number. Time at maximum was more related to viscosity. Then we went on to define the golden operating envelope, that is the golden batch recipe. So the golden envelope combines the key condition for consistent pulp quality, so SO2 to wood ratio, controlled SO2 levels, optimized acid dosage, moderate cook duration, and time at maximum temperature. So here chemistry can be implemented with oil, but time at maximum temperature should be implemented for each digester. And this can be further extended to bleaching process as well, with more context. Now remember, this is just the starting, not the destination. Because this golden batch golden batch analysis was the descriptive foundation. The next step would be predictive control, where we actually see the parameters real time, and then we can actually predict, or we can actually create alerts if viscosity or kappa numbers are going out of range. Then the next step would be prescriptive control, where we actually recommend what the dosages or what the operating range for each parameter should look like. So 4 key takeaways that we can take from this case study is that the kappa number, only 23% of the time kappa number and viscosity were in ideal range. So this is not something equipment related problem. This was the operating strategy that can be easily optimized. This strategy is easily replicable without any capital investment. And foundation of AI is foundation for AI. And fourth is we believe that the biggest bottleneck towards AI is not any algorithm, it's the data foundation. Thank you.